analysis. So here are two survey papers that cover much of the material I want to talk about today. The reason I didn't put a source for the second one is you can find it in the archive, I'm sure. It's because she only wrote one paper with that title. But Cliff wrote two papers with this first title, so it's sort of like football teams in Canada, I guess. They're all named Rough Riders. Okay, so today I want to talk about Gromov invariance and once again try to prove the Meng-Taub's theorem, or equivalently this knot surgery formula, from the point of view of symplectic topology. So, okay, so let's start with suppose we have a symplectic 4 manifold. And so omega is a symplectic form, so that means it's a closed 2 form on X, and omega wedge omega is never 0, never identical, however you say this. How's that? So, so it's non-degenerate. So, so so it can be shown that it's a standard fact that every symplectic manifold has admits an almost complex structure. And it turns out that it's best to study almost complex structures that are nicely compatible with omega. So that means that, so compatible almost complex structure means, first of all, that it's omega is J invariant, and also that omega of J V is positive. Okay, so this means that that omega, oh, you can't see it. Sorry about that. Can you see? You can't see the bottom line, huh? So that means that omega of J blankety blank is a metric on X. Okay? Okay, so a two-dimensional submanifold sigma, so now always embedded in X, but not necessarily connected, is J holomorphic provided J preserves its tangent space. So if that's the case, then it turns out that omega restricts to, J restricts to give you an almost complex structure on sigma, and omega restricts as a symplectic form on sigma. And in fact, you can think of sigma as, so J is on sigma, J is integrable, and so you can think of sigma as coming from an actual embedding into X, which is holomorphic with respect to, the structure you've induced on sigma and J. And so so sigma is often called a J holomorphic curve. And the point of Gromov invariant is to count pseudo-holomorphic, J-holomorphic curves in X. Notice that since omega restricts to will restrict to a symplectic form on sigma, sigma has to be oriented. And since J takes the tangent space of sigma to the tangent space of sigma, if we use this metric to define that, given by omega and J, to define a normal direction, then J will also preserve the normal bundle, and so you get an adjunction formula, just like for a holomorphic curve in a complex surface. And the adjunction formula reads 2G minus 2 is the self-intersection of sigma plus K dot sigma. So now, so here G is G of sigma, genus, and K. Okay, well, since we have an almost complex structure, the tangent bundle now inherits a complex structure, and so it has Chern classes. So you can think K is the element of H2 given by minus C1 of the tangent bundle. Okay? So this C1 depends on the compatible J. I mean, it depends on choosing a J, but as long as J is compatible, it doesn't depend on it. Okay? Okay, so now let's fix a homology class. And ask for a compatible, almost complex structure, J, let's try to find all the J holomorphic curves that represent A. So this, so define M of A, maybe M sub X of AJ to be the moduli space of holomorphic, J holomorphic curves representing A. Okay, so this space has formal dimension it's always even, and it's A dot A minus K dot A. Okay, so dA is 1/2 of this. Before I say anything else, let's think about Kähler surface. So in a Kähler surface, we know something about the Seiberg-Witten invariant. We know that, at least we know that K has a non-trivial Seiberg-Witten invariant and minus K has a non-trivial Seiberg-Witten invariant. And if X is this Kähler surface, well, look, minus K can't possibly be a holomorphic curve, but K probably is, and in fact, turns out that it is. So, and somehow, you know, zero is somehow trivially a holomorphic curve. So, I want to look at a linear function that takes sort of from H2 to H2 that takes K to K and 0 to minus K. And so this is the function A goes to 2A minus K. Okay? And just let's so let's calculate the dimension of the Seiberg-Witten, the moduli space of solutions to the Seiberg-Witten equations that have this as C1 of its spin C structure. Okay? So the dimension of the Seiberg-Witten moduli space with C1 of S equals 2A minus K is going to be 1/4 of 2A minus K squared minus 3 times the signature plus twice the Euler characteristic of X. And this number here is, that's C1 squared. Yeah, this is C1 squared. So that's the same as K squared. Yeah, so here we have 1/4 of 4A squared minus 4A dot K plus K squared and then minus K squared, okay? In other words, we get A squared minus A dot K, which is 2dA, okay? So this simple calculation shows us that there's a chance that there's some relationship between, well, at this point, in hindsight, it's completely obvious, right? But anyway, so here's a relationship. Okay, well, this moduli space, MAJ for compatible J is typically a compact manifold, except when A is represented by a multiply covered torus, and I'll try to explain this in a few minutes. So now, to make my life simple, let's assume that X is a minimal symplectic manifold. So we're going to, so this means no symplectic two spheres of self-intersection minus 1. Okay? So, these exceptional spheres can be dealt with, and in fact, in the article I listed by Dusa McDuff, she spends quite a bit of time talking about these things. So if you want to learn more about exceptional spheres, that's a good place to look. Okay, so let me so let me tell you how to define the Gromov invariant. So this is sort of the short version. So again, A is this homology class, and the adjunction formula tells you that a pseudo-holomorphic curve representing A has a prescribed genus. So from the adjunction formula, you know that G of A is A squared plus K dot A divided by 2 minus 1. Okay? So now let's assume first that D of A is 0, and so if D of A is 0 and the genus of A is either greater than or equal to 2, or G of A equals 1, and A is a primitive class. Meaning indivisible. Liberty and justice for all. Okay? Then, since D of A is 0, this moduli space is a zero-dimensional compact manifold, and we count the points, and that gives us the Gromov invariant. Of course, you have to assign a sign. So we count, better not write on there. So count points of M X A J for a generic compatible J with signs. And the signs are determined by Taubes. They're determined by a linearization of D bar in the neighborhood on sigma, and somehow you have to look at a path of operators until you hit a complex operator, and then you count the spectral flow from the complex operator back. I learned yesterday not to be so technical, so I'm okay, so this is dealt with in the Taubes paper that I wrote. Yeah, but so the sign comes from a spectral flow. Okay, so now what if D of A is positive? If dA is greater than 0, then your moduli space is an even dimensional compact manifold of dimension 2dA. And so what you do is you pick dA points in your manifold and demand that your holomorphic curve run through those points. Each point will give you introduce two-dimensional restriction. So it'll cut down the dimension of your moduli space by 2 for every point. So then choose dA points, x1 through xd, and count the number of points in mx, what can we call it, aj, x1 through xd, meaning the space of J holomorphic curves containing all the xi. So now if, okay, there's several cases I haven't talked about. So what about 0? If A equals 0, if A equals 0, then it's just by convention you define the Gromov invariant of 0 to be 1. And this sounds completely silly, except that later on we're going to see it's important. For, finally, these tori. So tori that aren't primitive. Okay, so here, here's the problem. So suppose you have, I don't know how to draw this. So here's a torus representing a class B, and perhaps the torus A covers it locally. This can happen. Think about, even disjoint, right? So think about in an elliptic surface, you might have a handful of fibers that are very close to some other fiber, a multiple fiber, yeah? And so you might have a sequence of such holomorphic curves that converge down to a multiple cover of B. So if you think of this in terms of curves, you have some curve, J holomorphic map from the torus into X, representing the class B. So this is some embedding representing B. And then you have an M-fold cover of the torus. And the composition then might be the limit of J holomorphic curves representing A, which is M times B. Okay? And so the problem is that a torus, if you're going to build some kind of a count, the torus need not only contribute to its own Gromov invariant, but it contributes also to Gromov invariants of multiples of itself. And so then the question is, how does it contribute? I gave it the office. So Taubes has completely worked this out. And so there are these functions, Taubes counting functions. And you might guess that such calculations might be super complicated, but in fact it turns out the answer is quite simple and elegant. And so here's one so Taubes papers are one place to look for this. Another place where this is beautifully described is in a paper of Ian and Parker. Let's see which. It's called The Gromov Invariance of Ruan, Tian, and Taubes. And so let me tell you the answer. So the answer is there are 8 counting functions. But you sort of only have to know 4 because they pair off as inverses of one another. The 8 counting functions are denoted f plus minus I, where I one of the first 4 integers. So here's what this corresponds to. This plus or minus, this corresponds to the sign that the torus got from this spectral flow that I was talking about before. So there was an operator D that was obtained from the linearization of D bar. Its spectral flow gives you a plus or a minus. The I corresponds to its twisting. So there are 4 real line bundles over a torus. H1 with Z2 coefficients is Z2 plus Z2. So there are 3 non-trivial real line bundles. And it turns out you can twist this operator by any of these 3 line bundles and look at the spectral flows corresponding to those twisted operators, and then you can count how many have non-trivial spectral flows mod 2. So there may be all 3, maybe none. That's what these numbers are. In general, you expect none. If you have a torus that has a neighborhood where J is integrable, then you get one of the functions f plus or minus 0. So let me tell you what these functions are. So first of all, f minus I is 1 over f plus I. So we only have to know 4 of the functions. And f plus 0 is 1 over 1 minus t. And I don't know the others. I'll have to copy them. F of plus 1 is 1 plus t. F of plus 2 is 1 plus t over 1 minus t. And f of plus 3 is 1 plus t times 1 minus t squared divided by 1 plus t squared. So here's what these functions mean. So you should expand these in a power series, and then your torus, think of your torus as corresponding to t, and then it contributes to multiples according to the coefficient that it contributes to mt corresponding to the coefficient of t to the m. Okay? So for example, f of plus 0 is 1 plus t squared and so on. So if you have a torus with an integrable neighborhood, it contributes 1 to its own count, of course, and then contributes 1 to every count of every multiple. Okay? Okay, so let's use this to calculate the Gromov invariant of En. With a little cheat. Okay, so first of all, am I twitching? It's always possible. It's always possible to introduce. Where's Michael Usher? Can you do this with all I or just with plus 0 and minus 0? I've learned this from Tom Parker. So you could always introduce plus 0, minus 0 pairs. Can you produce plus I and minus I pairs for all I? That might be harder, huh? Given, so in En, for example, in E2, okay, let's think about E2 for a second. This is the K3 surface, and one fact we know about the K3 surface is for generic complex structure, this gadget has no curves. Yeah? On the other hand, we can get ourselves an almost complex structure which contains 1 plus 0 torus and 1 minus 0 torus in the fiber class. Yeah? So it's possible to do this. It's fiber, fiber. I'm assured by Tom Parker, at least several years ago, that this is a fact. However, I don't know. See, these, yeah, okay, you'll see in a second. So let me point this out in a second. Okay, so here's what we want to do. So what I want to do is talk about a relative Gromov invariant. So let's remove the neighborhood of a J holomorphic torus. Yeah? In the fiber class. And I want to look at E2 minus such a neighborhood where J is integrable. Well, what should its Gromov invariant be? Well, see, because generically there are no holomorphic there are no holomorphic curves in K3, one can give a kind of limiting argument that shows its Gromov invariant should be 1, meaning 0 always has Gromov invariant 1, and any other class should have Gromov invariant 0. Okay? So I'm going to, again, write the Gromov invariant as a polynomial. Okay? So now let's write down the Gromov invariant of E2 minus NF. And now there's a gluing formula again. You can look at work of Ian Allen Parker. Okay. But here we have a plus 0 torus neighborhood. So its Gromov invariant is 1 over 1 minus t. So that means that the Gromov invariant of K3 minus this neighborhood is 1 minus t. Okay, so got 1 minus t. Okay, well now, once you know this, you can go through the same song and dance. It's not a Macarena this time, it's some other dance that I was talking about on Monday, I guess, when I computed the Seiberg-Witten invariance of the elliptic these ENs. Because since you know this relative invariant, you can now write, yes. It has plus. It means J is integrable, and the sign you get is plus. Okay? Yeah. And now, I guess maybe I should have done this first. So now let's look at the Gromov invariant of E1 minus NF. Maybe this is the calculation I should have done first. So now that shows that each of these is 1. So that the Gromov invariant of E1 is 1 times the Gromov invariant of n of the fiber, which is 1 over 1 minus t. We know the Gromov invariant of E2 is 1. The Gromov invariant of E3 is the Gromov invariant of E2 minus the neighborhood of a fiber times the Gromov invariant of E1 minus the neighborhood of a fiber. This is 1. This is 1 minus t, so we get 1 minus t. And in general, you just keep doing this and you compute the Gromov invariant of En as 1 minus t to the n minus 2. At this stage you say, gee, this is virtually the Seiberg-Witten invariant. There's only sort of a translation. Remember the Seiberg-Witten invariant of En was t minus t inverse, or let's write it as t inverse minus t. It'll look closer to the n minus 2. So I only, yeah. Okay. One thing that, I didn't notice until I was thinking about this last night is the following. So when you make an argument like this, remember the theorem of Doug Park that I talked about on Monday that said that if H1 of the H upper 1 of the complement of a tubular neighborhood of a torus, if the map from that onto the boundary 3 torus of this tubular neighborhood, H1 of that has no torsion in its co-kernel, then the relative Seiberg-Witten invariant is the absolute Seiberg-Witten invariant times t minus t inverse. Well, that makes it look like, and in fact we'll see in a minute, that it makes it mean that that co-kernel condition will mean that such a torus is a plus 0 torus in the symplectic situation. Okay. Okay, so the reason I'm giving this lecture today is because Cliff Tubbs has proved such beautiful theorems about symplectic 4 manifolds. So let's first start with some facts that Tubbs has proved about the Gromov invariant. So suppose we have X as a minimal symplectic 4 manifold with B plus greater than 1. Okay, again, minimal just means no spheres of self-intersection minus 1. Then, first of all, the Gromov invariant of 0, well, that's 1. And the Gromov invariant of the canonical class is plus or minus 1. So in particular, the canonical class is generically represented by a pseudo-holomorphic curve. 2, if the Gromov invariant for some class A is non-zero, then this number dA, or twice dA, which is a squared minus k dot a, is always 0. So if the Gromov invariant is non-zero, then the moduli space was already 0-dimensional. And correspondingly, the moduli space of Seiberg-Witten solutions corresponding to the spin C structure 2a minus k, we saw that's also 0-dimensional. Yeah. 3, the Gromov invariant of A is the same as the Gromov invariant of k minus A. well, up to a sign, sorry. And 4, so if the Gromov invariant of A is not 0, then A dot the, and however you want to think of this, maybe think of the A dot, since we're talking about homology, the Poincare dual of the class representing the symplectic form, or if you like, integrate the symplectic form over A, however you want to think of that, is non-negative and less than or equal to k dot omega. And actually, equality at either end, unless equality at either end means that A equals 0 or k. So the key fact that sort of underpins all this is, I think, is clearly one of the great achievements of 4 manifolds. So this is the theorem of Taubes that says with appropriate orientations, and again, so B plus greater than 1. With appropriate orientations, the Gromov invariant of A is actually equal to the Seiberg-Witten invariant of 2A minus K. So in particular, notice this tells us that the Seiberg, right? So we said it's sort of a trivial fact. So we, by convention, define the Gromov invariant of 0 to be 1. But this theorem is telling us then that means that the Seiberg-Witten invariant of minus the canonical class has to be 1. Okay, and when B plus equals 1, the same thing, well, when B plus equals 1, then the Gromov invariant of A is, so when B plus is 1, remember we have these Seiberg-Witten plus, Seiberg-Witten minus, depending on an orientation for the homology. So the orientation in that case should come from the symplectic form omega. And so the Gromov invariant of A is Seiberg-Witten minus of 2A minus K, where again, so this means, Seiberg-Witten minus means that C1 of this class, 2 pi C1 minus the whatever perturbation term you use, mu, dot with omega should be negative. That's what the minus means. And this is true for all classes A which intersect with any exceptional sphere bigger than or equal to minus 1. So such that A dot E is greater than or equal to minus 1 for all, let me just write exceptional spheres E, meaning symplectic spheres of self-intersection minus 1. Okay? Okay. Okay. Snort. So what I'd like to do in the last few minutes is to talk about, one more time, about a version of the Meng-Taubes theorem. So, I promise this is the last time I'll try to talk about a proof of this. Although Peter tells me there's one more proof he's got. Maybe he'll talk about one. So suppose we have a three-manifold that fibers over the circle, and its fiber is an oriented, so this is oriented, closed three-manifold, and this is a fiber bundle. So fiber's an oriented surface. Now anybody who's seen Tubbs talk about this has seen the following construction. So he argues that it's, so let's let lambda be the volume form on the circle, on the base. And so what I want to do is construct a symplectic form on S1 cross Y. And so the way to do this is you choose metric so that P is harmonic. Make P harmonic, and then pull back lambda, so now we have a 1 form on Y3, and well, maybe I should think of pulling it back to S1 cross Y. So think, that pulls it back to S1 cross Y. And then think of, let's let theta be, you project on the first circle and pull back its volume form and call that theta. So here what we have is a two-form sort of, if we think of S1 cross Y as a fiber bundle over a torus, S1 cross S1, we've got a two-form in the base direction. And then we add the star, the Hodge, three-dimensional Hodge star of P star lambda. That gives us a two-form in the fiber direction, and that's a symplectic form. Symplectic form on S1 cross Y. Okay, so so let's now restrict to the case where Y is equal to mk for k a fiber dot. Remember, mk, I mean zero surgery on this fibered knot. Then mk has a fibration over the circle whose fiber is a closed surface, whose genus is the genus of this fibered knot. Okay? Right, so let's let F be its monodromy. So this is a bundle over the circle. It's sigma cross I mod F. And what's the second homology of S1 cross MK is, so remember MK is a homology S2 cross S1, so this is Z plus Z, and one of these Z's is the fiber class, so sigma equals fiber. And the other class is generated by S1 cross the meridian to the knot, this torus T. And the goal is to compute the Seiberg-Witten invariant of this manifold by using Taub's theorem, that Gromov equals Seiberg-Witten. Okay? So what we want to calculate is we want to calculate Seiberg-Witten minus S1 cross MK. And what we've seen before is we really need to calculate even multiples, the Seiberg-Witten invariant of even multiples of T. So if you want to argue against anything with a sigma coming into it, having a non-trivial Seiberg-Witten invariant, well, you'd like to say just use the adjunction formula. But you know, this is b plus equals 1, so you can't quite do that. But what you can do is use the gluing formula and do some trickery, glue into a K3 or something, and then argue, then use the adjunction formula. So you can do that. So these are the classes. At any rate, we've seen this already. These are the classes we need to calculate. Okay, so remember, how does Gromov equal Seiberg-Witten work? So here's Gromov side, here's a Seiberg-Witten side, and a class A here has the same Gromov invariant as the Seiberg-Witten invariant of the class 2A minus K. So 2RT, RT has the same Seiberg, maybe we should call it NT. NT has the same Seiberg-Witten invariant as has the same Gromov invariant as the class 2NT minus K. And it's easy to calculate using the adjunction formula on this manifold. The adjunction formula now, not the adjunction inequality, it's a symplectic manifold. That canonical class is just 2G minus 2 times T. Yeah? So just, you know your canonical class is some multiple of sigma and some multiple of T, intersected against sigma, intersected against T, and you'll see this. Okay? Okay, so this is 2n minus 2g plus 2. So there's this correspondence we have to worry about. Okay, so here's the theorem. So the theorem, again, this is due to Taubes, is that, Seiberg-Witten minus of S1 cross MK. So again, this is the sum over n of Seiberg-Witten minus of 2nt times t to the n is equal to the determinant of t inverse minus t f star divided by t inverse minus t squared. So what this is this is really t to the 2 minus 2g. Remember, 2 minus 2g times the characteristic polynomial of f star, so times the determinant of identity minus t f star divided by 1 minus t squared squared. So I hope this will show. So you use the first two g's up in the determinant here, which is a matrix of 2g by 2g, and the plus 2's become minus 2's down here. Clear that. Okay. Now, so now here's the formula for. You can check very quickly. This is just the Bang-Taubes formula, because the numerator there is, it's a symmetrized Alexander polynomial, on the one on the left here. Okay. Okay. So suppose we choose a metric. We want to choose a nice metric on S1 cross MK. So let's choose a metric which is a product in the the theta and the lambda directions. So sort of metrically what we have is S1 cross MK. We have the S1 looks like I mod the 0 equals 1, and the MK looks like sigma cross 0, 1 mod F. And here's the formula I wanted to write down. So if, suppose you have some cotangent vector in S1 cross MK, then you can write a formula for J. It's minus star of omega wedge alpha. So then using this, it's an exercise to see that in sigma cross I mod, so here's, I've drawn the sigma cross I part. We want to ask what curves can represent n times t and be J holomorphic. So what these curves have to look like is straight lines that run through this product. So to represent nt, we have to have n lines that run straight through the product, and they have to close back up to give us a closed loop. So we get points in sigma. So once again, we get this kind of dimensional reduction. We get points in sigma. These points must correspond to an orbit of F, which consists in which lives in the fixed point set of F to the n. So this has to be an orbit of F. So these points in orbit of F, a finite orbit of F, contained in the fixed set of F to the n. Okay, so we want to count such curves. So the first thing is, what sign should you give to this? I mean, I didn't describe the spectral flow. I didn't describe the operator. How the heck am I going to convince you what the sign should be? But here's, so first of all, yeah, I'm almost out of time too. So let me say that you could do one of two things. So first of all, you convince yourself that these tori are all of type 0. They're plus 0 or minus 0. You can convince yourself of that by one of these co-kernel arguments that I was talking about from Doug Park's theorem. Just look, so that you can actually calculate, no problem at all. So each of these corresponds to F plus 0 or F minus 0. And there's another kind of sign that you assign, that's related to this situation. After all, you've got a fixed point set of Fn, and so you could ask, what should I attach? Suppose I were trying to compute the Lefschetz number. Should I attach a plus or a minus? Well, if you were thinking about the Lefschetz theorem, then you would attach the sign of the determinant of 1 minus df to the n, right? And so let's call that, so if you have a point, if one of these points is called q, let's call this epsilon q. So that's the sign corresponding to the torus that runs through the fixed point q. Yeah? And so then what you get is a torus of type epsilon q comma 0. So this means that you should assign to it 1 minus t. Well, not really. This t is representing n times capital T. So we should attach 1 minus t to the n. Now if it's a plus, it should be 1 minus t to the n inverse. If it's a minus, it should be, yeah, so it should be minus epsilon q. But we've overcounted because, you know, in nt, there are n of these points at the end. So if we're only counting according to the points in the fixed point set, we should just count, we should divide by n, and then each point contributes 1 minus t to the n to minus epsilon q over n to the product. Okay? So, and this still might not be right because we should only count it a point sort of the first time it appears. If it's a fixed point set of f cubed, we shouldn't also count it when we go to f to the sixth. Yeah? So you let Sn be the set of points q such that, you know, q is in the fixed set of f to the n and not of f to the m for m between 0 and n. Okay? You only want to count it once. And so then what you do is you take the product of over all q and Sn of these 1 minus t to the n to the minus epsilon q over n, and you have to take the product over all n, and well, there's something else you have to do, because remember, the Gromov invariant isn't the same as the Seiberg-Witten. Say the Gromov function is not the same as the Seiberg-Witten function because there's the correspondence there. Nt corresponds to 2n minus 2g plus 2t. So this means if you want to calculate Seiberg-Witten of t, you should calculate Gromov of t squared, because that's where the 2n's coming from, and then there should be an overall factor of 2 minus 2g, t to the 2 minus 2g. Okay? So this is just accounting for the translation. So there's this t to the 2 minus 2g, and the claim is this is the Gromov invariant, so therefore, you know, translated from the Gromov invariant, so therefore it's a Seiberg-Witten minus of t. So here's your Seiberg-Witten function. And now it's just some, okay, from this point, Taubes attributes his, says that Bott told him the rest of the proof. And here's the proof in a nutshell, is you take logarithms of both sides and play around a little bit. And you see that you end up calculating some Lefschetz numbers. You apply the Lefschetz fixed point theorem, and you're done. So I wrote down that proof, and you can see it in those notes, but you surely don't want to see me copy that proof onto the board. So why don't we stop here?